Okay, today we're going to learn about polar functions and specifically polar coordinates. If I have a Cartesian plane in the point 2, 2, I can name this in 4 different ways, or actually an infinite amount of ways, but I'll just name it 4 ways here. You start out with r and a theta, and if I have the point 2, 2, my r is going to be the distance from the origin to the point 2, 2 right here. And that is 2 square root of 2 using Pythagorean theorem. And so normally you'll start off with the angle, so you go up pi over 4, and then the distance is 2 square root of 2, so this is where this point comes from. This point right here comes from going negative 7 pi over 4, so all the way around, and that's also positive 2 square root of 2. I can also name this point using a negative 3 pi over 4, which would be back here, and it would normally be, if this was positive 2 square root of 2, it would be like this. But since it's negative, that reverses it, so that's another way to name this side right here. And then we can also go around 5 pi over 4 and negative square root of 2 over 2, which would be like this. No. Right there. And then negative square root of 2 over 2. Alright, we can also convert polar equations to rectangular equations or Cartesian equations. And these are the 4 main formulas that we'll use to do that. So here's an example. Replace the polar equation by an equivalent Cartesian equation. Start out with r equals 4 cosecant theta. So we can also rewrite this as r equals 4 over sine theta, and then when we multiply sine theta on each side, we end up getting r sine theta, which is y, equals 4. Alright, so you can also find slope of polar functions, and if we have the problem find the slope of the tangent line to the curve r equals 2 plus 4 sine theta. These are just a few things that we know. We know that dy dx equals dy d theta over dx d theta. This is just defining this polar function parametrically. And we also know that r equals f of theta, and x equals r cosine theta, and y equals r sine theta. So, if we want to find dy dx, we know that r equals f of theta. So, using some substitution and the product rule, we end up getting f prime of theta sine theta plus f of theta cosine theta over f prime of theta cosine theta minus f of theta sine theta. And when we do some more substitution and plug this equation here into the dy dx, we end up getting this really big equation, and it can be simplified down to 2 cosine theta plus 4 sine 2 theta over 4 cosine 2 theta minus 2 sine theta using some double angle formulas that you should have learned in trig. We can also calculate area of polar coordinates using this equation here. Area equals the integral from alpha to beta of 1/2 r squared d theta. So if we're given a problem asking us to find the area of the region represented by r equals 2 minus cosine theta, we'll just use this formula here. It's not too complicated. And normally with these problems you can use your graphing calculator. One key note that you want to make sure you do with this is you need your x to y ratio needs to be 3 to 2. So as you can see here, I go out 6 on each side for x and up 4, so that's 3 to 2. When you graph these, so that you make sure you get an accurate picture, and then you just use this formula here. The hardest part about these problems is finding our alpha and our beta, but if you watch the graph of this, the area sweeps out starting at 0 and it ends up at 2 pi, so these are our alpha and beta. And then we just plug in our r, and we square that and multiply it by 1/2, and we end up getting 14.137. Alright, lastly we're going to find the area between polar curves. And the formula for this is the integral from alpha to beta of 1/2 r2 squared d theta minus the integral from alpha to beta of 1/2 r1 squared d theta. And then you can simplify that to the integral of alpha to beta of 1/2 r2 squared minus r1 squared. And the r2 represents the outer function and the r1 is the inner function. So when it says find the area inside the cardioid r equals 2 times 1 plus sine theta, and outside the circle r equals 2 sine theta. I did a rough sketch of this here, and here's the cardioid, looks like a heart, and then here's the circle. So we're looking for this area right here. One thing you have to be careful with on this problem is that the circle sweeps out its area from 0 to pi instead of from 0 to 2 pi. So if you would have used this equation here and said your alpha was 0 and your beta was 2 pi, you would have gotten this problem wrong. But basically we just did the cardioid first and plugged that into the formula from 0 to 2 pi, and then we subtracted the circle right here from 0 to pi, and we ended up getting 15.708.